So now in this lecture, we shall be discussing about the design of the cantilever beams. So when we are talking about the cantilever beams, it means that the one end is basically fixed and the other end is not supported. So to start with that discussion, first of all, we can start discussing with the theoretical example, and then we should be doing the same in the ETAP software, so that you can understand how the cantilever beam bending moment can be calculated and how the design can be done. So let us say the span of this particular beam is 3 meters, and on the left it is basically fixed, and on the other end it is free. And yeah, so considering that permanent load is basically 5 kN per meter, and imposed load is also 5 kN per running meter, and the load combination that is being implemented is basically 1.2 times dead load plus 1.5 times the 1.2 times the permanent load and 1.5 times the imposed load. So with that equation, basically the bending moment that comes as approximately 62.4 kilonewton meter, and the shear force approximately comes out to be 41.6 kilonewton. So to start with that calculation, first of all, we know that, let us suppose the beam section that we are considering is, let us say, UB 250 into 32, and the steel gauge is basically 300. That is the thickness of the material as it is like thickness of the flange and the thickness of the web. So the maximum thickness is approximately 8.6 mm. So the Fy considering 300 grade can be considered as 320 Newton per mm square, as the thickness is very less. Tensile strength, although it shall not be used in the calculation, but for the records it can be used as 440 Newton per mm square, and modulus of elasticity can be used as 2 into 10 to the power 5 Newton per mm square. Thickness of the web is 6.1 and thickness of the flange is basically 8.6. So we do have to consider the maximum thickness only for the yield stress calculation as per the grade of the structural steel. Capacity factor, as we know that for the bending it is 0.9. So first of all, we do the same process, that is, we do need to calculate the section slenderness and check that whether the section is compact or non-compact or slender. So in here, if we start with the equation that our flange slenderness is basically Bf minus Tw divided by the 2Tf and Fy by 250. So this value comes out to be 9.2, and the limit is 16 that we had already discussed in the earlier lecture. And if we're talking about the web slenderness, the web yield slenderness limit considering d1 by Tw, that is the depth of web divided by thickness of the web, it comes out to be as 115. So the section slenderness is basically what we can say as 9.2, and section plasticity limit, that is basically 9. So with that, we can say that the yield slenderness limit is that was approximately 16. So our lambda SP is less than lambda S, that is 9.2, and that is less than lambda SY, that is the yield slenderness limit. So with that, we can say that the section that we are using, that is basically non-compact section. So in contrast to the earlier lecture where we had discussed compact section, in this lecture we should be discussing about the non-compact section. So shear capacity of the web and shear yield capacity and shear capacity. So all of this we should be discussing in the later stages, but first of all we shall start with the design of the bending moment itself. So just to give you an example, that is, if we are talking about the non-compact section, it is not that the full section we can say shall be utilized. We shall be talking about the partial factor utilization. So that we shall be discussing here. So in here you can see that effective compact section modulus is basically minimum of Sx and 1.5 into Zx. So effective sectional modulus Ze, that is basically Zx plus this particular formula, that is lambda Sy minus lambda S divided by lambda Sy minus lambda Sp, and that is again multiplied with Zc minus Zx. Zc, as we know, that is effective compact section modulus, that is 397500 mm3. So if you're talking about this particular equation, that is effective compact section modulus, that is minimum of Sx and 1.5 of Zx. So we can simply refer to the property manual here. So in here you can see that for 2B UB and 31.4, our Sx is approximately 397. Basically, that is again multiplied with we can say 1000 here. So, and the Zx, that is approximately 354. So considering that, what we have to do is that either the minimum of 1.5 into 354 or 397 into 10 to the power 3 mm cube. So if we go into the exact, the value, we do get this particular value, that is 397500. As 1.5 into 354, that is approximately, we can say as uh 15 3 is 40, yeah, approximately 525 triple zero mm cube. So with that equation, we can say that the ZC is approximately 397500. So after that, if we are talking about the what we can say as the effective section modulus, so that is again the value that we are using here, Zx plus this particular equation. So lambda sy minus lambda s that we have already calculated here. So lambda sy is 16 and lambda is approximately 9.2 divided by lambda sy minus lambda sp. So lambda sy is again 16 minus lambda sp is approximately 9. So that ratio needs to be multiplied with zc minus zx. So zc is approximately 397500 and zx, as we know, that is approximately 345 000 mm cube, the one that we had discussed here. So with that, you can find out the value of effective section modulus as 396,263 mm cube. So nominal section moment capacity, that needs to be multiplied with this, not with this. So earlier when we had discussed about the compact section, we were dealing with this particular value. But considering that the section is non-compact, we have reduced this value from this to this. So that is the way we works with the non-compact or slender section, by reducing the effective sectional modulus by multiplying with this particular ratio. So this is the formula that is given in AS 4100 itself, clause number 5.2.4. So here we can see that for the compact section, it is saying that effective sectional modulus ZE shall be lesser of S or 1.5 Z. So S and 1.5 Z is this particular value. So this is the S, and Z, that is particular, that is also given for all the properties here. But if we are talking about the non-compact section with lambda sp less than lambda s, lambda less than lambda sy, the effective section modulus shall be this particular value, that is Z plus this particular equation that we had already discussed. So I hope the concept is clear to you. So here also you can see that the code is also guiding us regarding how we can design the slender sections also. But before explaining you, as I said, it is never recommended to have the bending members as the slender section. So in here you can see that Z is basically Z into multiplied to lambda sy by lambda s. So with that we reduce the effective section modulus. But for section where slenderness is determined by the value calculated for a flat plate element with maximum compression at an unsupported edge and zero stress at the other edge, and which satisfy this particular equation, the effective section modulus shall be calculated at this particular value. And for the circular hollow section, obviously the formulae are different when we are talking about the AS 4100. So as I said, it is never recommended to use the bending members as the slender sections. So after that, if we can come back to the example that we were calculating. So nominal section moment capacity is Fi into Ze. That is, we multiply 320 Newton per mm square with Ze, this particular value, to find out 126.8 kilonewton meter. And again we multiply it with the phi, that is 0.9. So multiplying it by 0.9, that gives us approximately 114.1 kilonewton meter. So after that, if we're talking about the segment with the full lateral restraint, so in here we can see that ms1 and minimum, that is 0, and the maximum bending moment is 62.4, and the end moment ratio is basically 0. So we can say that maximum segment length following clause 5.3.2.4, that is approximately 2360 mm. So instead of, we can say, following 3000 mm, the maximum segment length that can be considered if we are talking about the full lateral restraint is 2360 mm. So if we talk about the AS 4100 2020 code, you can see that the main title is basically segment with full lateral restraint. So considering this particular value, that is segment with full or partial restraint at both hand, and following this particular formula, that is L by R Y, that is less than or equal to 80 plus 50 into beta m multiplied with square root of 250 by Fy. Now we have already calculated beta m as basically 0. So that is nothing but, this whole equation comes out to be 0. Square root of 250 divided by Fy we already know that is approximately 320. And Ry we can see it from the property table manual here, the one that we were discussing here. So in here they've already telling you about the value of the Ry. So to putting those, our maximum segment length comes out to be 2360 mm. So segment is not considered to have full lateral restraint. So if we can say member capacity of segment without full lateral restraint, so that is the same formula that we had discussed. If we are talking about the earlier lecture, we were discussing about the member with laterally unsupported behavior. So these are the different values, are the different parts of the, we can say, bending moment curve. So this is the bending moment curve. So moment at quarter point of segment, so that is approximately, we can say, 35.1. Member at moment at center line of segment, that is approximately 15.6, and at 3/4 point of segment, that is 3.9. So in here, that is approximately, we can say, as 35.1. At this particular point, that is half, it is approximately 15.6, and at here it is approximately 3.9. So considering that, the maximum bending moment is approximately 62.4 here. So after that, the moment modification factor alpha m, that is minimum of 1.7 into mm star, and divided by square root of m2 square plus m3 square plus m4 square, or the minimum of 2.5. So this value turns out to be higher, so that is why we are adopting this particular value as 2.5. After that, KT, KL and KR we have assumed as 1 for, we can say, the theoretical assumption only, but as I said, that load height factor, that is usually 1.4 in practical cases. So effective length, that is approximately 3000 mm, and reference buckling moment, we have already discussed that pi square e pi square e iy divided by le square multiplied with g into j plus pi square e into iw divided by le square. So le is the effective length that we already calculated as 3000 mm. E modulus of elasticity, that we have already know that 2 into 10 to the power 5. I y and iw, so these are the the values that are dependent on the, we can say, section itself. So iw is the warping constant, E we already know, G is basically the we can say shear modulus, and J is basically the torsional constant. So putting all of these values, the value comes out to be 154.7 kN meter. After that, slenderness reduction factor, so alpha s. So alpha s can be calculated from this particular equation, that is square root of ms by moa square plus 3 minus ms by moa. So this is the value of moa, that is the reference buckling moment, and we have already calculated the value of the ms. So ms we have already calculated as 126.8 kilonewton meter. So putting all of these values, the alpha s value comes out to be 0.641. So multiplying, we can say, 0.641 with the alpha m, that is 2.5. So, or the minimum of 1. So alpha m into alpha s comes out to be greater than 1, that is alpha m is 2.5 and alpha s is 0.641. So the code says that, okay, if the value comes out to be higher, still you have to proceed with the maximum of the 1 only. So MB, we can say, more or less comes out to be same as the one that we have calculated here, that is MS. So this value comes out to be 126.8 kN, which when multiplied with 0.9, that is the capacity reduction factor, comes out to be 114.1. So the bending moment in our case, that is coming, is approximately 62.4, but the capacity of this section, that is approximately 114.1. So this member is safe against the, we can say, bending moment. After that, we shall talk about the shear capacity also. Shear capacity we already discussed, that is very simple. That is what we have to do is that we have to simply calculate the gross cross section area of the web, and that is coming out as approximately 1537 mm square. So the depth of the web that we are having, so the total depth that we are having is approximately 252, which needs to be multiplied with 6.1. So what we can do here is that we can simply multiply 252 with 6.1 to find out the gross cross-sectional area of the web, that is 1537.2 mm square. So 1537 mm square is the value that has been considered here, which needs to be multiplied with Fy, that is approximately 320. So 320 into 0.6 into 1537. So this value comes out to be approximately 295.1, which needs to be multiplied with 0.9. That is a capacity reduction factor to find out the design shear capacity. So that comes out to approximately 265.6 kilonewton. So after that, we can study the effect of what we can say as the interaction of shear and bending also. So we have already seen that the design shear capacity with bending, that is approximately 265.6, and we can say that the difference between the shear force and shear capacity, that is quite high, and the difference between the bending moment and bending moment capacity, so that is also quite high. So we can say that the curve that we had discussed in the earlier lecture, that is the danger part. So we are not in that particular area, so we are somewhat here, so we can say that we are safe. So after that, the deflection also that we can calculate, so it is coming out approximately, we can say 11.678, and the limiting deflection that we have assumed as 250, as the span divided by 250. So this is the basically the appendix B here. So that also we had discussed earlier. So beam supporting, we can say masonry partition, and for cantilever, the code is allowing, we can say the L divided by 250. So that is the value that has been considered here. So the value comes out to approximately, we can say limiting value is 12 mm, and the deflection in our case, that is coming as approximately 11.7 mm. So it is on the margin, and we can say that it is safe as per the deflection limits defined by the ES 4100. Now we can do the same, we can say calculation in the ETAP software also, to check how the software calculates and how we can do the actual analysis in the ETAP software. So we can select all of these properties here, and after that, as we know that the span is approximately 3 meter, so we can select number of grids as 2, and the spacing of grids in X and Y as 3 meters, number of stories as 1, and we can left click on OK. So we can select material properties here first of all, and we can left click on what we can say add new material, Australia steel, and grade 300 as thickness less than 11 mm. So we can left click on OK, as the thickness of the, we can say maximum thickness is 8.6. So here we can see that under the material property design data, the yield stress is 320 Newton per mm square. So that is also okay. And then again left click on OK. So after that, we can go to the define section properties and frame section, and then left click on, we can say import new properties, steel I. In here we can select UB 25031. So this is the section UB 25031.4. We can left click on modify show property, and this step is very important because from this particular option itself we can select the material properties correctly. So in here we do need to select AS3679.1 300 thickness less than 11 mm. So if we keep as it is, the material, or we can say section, shall be under design. So thickness less than 11 mm, and again left click on OK. So after that, we can go to draw beam column brace. So select UB 25031.4 here. So model the beam from this point to this point. So we can select object option here, just close this window here, and we can switch off the grids also. So this is the beam that on which we shall be studying and applying the loads. So we can select this particular node here. We can go to assign, joint, restraints, and we can apply the fixed node at this particular point. After that, in the study manual itself, we have selected the permanent load and the imposed load. So both of these values were 5 kilonewton per running meter here. So this is also 5 kN per meter, and the imposed load is also 5 kN per running meter. So we can go to the assign frame loads and distribute it. So under this option we can assign 5 kN per running meter, and under the life, that is the imposed action, also we can assign 5 kN per running meter. So after that we can go to the define load combinations also. So we can left click on add default design combo, steel frame design, and convert to user combination editable. So we can open this particular here. So this is one time dead. Second is one time dead plus live. 1 DL plus 1 LL. And this is simply one time dead load. Third option here is basically 1.35 time dead load. And the fourth option is basically 1.2 time dead load. Plus 1.5 time live load. So what we can do is that we can go to the analyze, and we can click on set load cases to run to switch off the model analysis, because we won't be running the model analysis here. So what we can do is that we can just to check the deflection here, we can go to the display and deform shape, and under that we can select the combo of one time dead load plus 1.1 times the live load. So we can see that the deflection is approximately 11.824 mm, and in the manual calculation that we have checked was approximately 11.68 mm. Yeah, so this is approximately 11.678. So more or less we can say that the results are comparable. And after that we can just click this option here, and we can select view and revise preference. So in here we can select all of these options here, and then we can select the design combinations also. So for the strength, it is automatically selected, and for the deflection, they are also automatically selected. And then we can just click on steel frame design. So again, there might be a difference that we are dealing with the different values of KT, KL, and KR. So what we can do is that we can select this particular value KL also as 1. And then again, we can left click on overrides, and then we can see that the major bending moment capacity that is coming is approximately, we can say, as 114 kilonewton meter, and moment modification factor alpha m is basically 2.25, and alpha s is approximately 0.646. So first of all, we can start checking with the value of the alpha m, and we can open the calculation again. So we can say that there is a little bit of difference in the calculated value of alpha m, and with this particular equation we had calculated as 2.5, and here it is considering 2.25. So what we can do is that we can apply the correction, but and after that slenderness reduction factor alpha s. So alpha s value, if also we are calculating as per the manual calculation, to coming approximately 0.641. So this is also comparable, that is 0.646. Yield stress, we know that is approximately 320 Newton per mm square. So by applying that, our value comes out to be approximately, we can say, 113.9713 kilonewton meter. That is a major bending moment capacity. And as per the manual calculation, it is coming in 114.1. So more or less we can say that it is coming approximately same. And the reason why alpha m value is not of much significance here, because if we are multiplying 2.25 also with 0.646, this number is higher than 1. So ultimately we alpha m into alpha s value, that shall be limiting to 1 only. So that is why this number is not changing even if we are changing the value of the alpha m. So we can left click on this particular, yeah, just a minute. We can do this, and then again we can check the values. So here we can see that the LTB, by changing the value of this LTB, that is KL, this value also changes. Yeah. So after that yield stress, we know the 320. So the major bending moment capacity, that comes out to be 114 kilonewton meter, which we can check in detail in this particular detailed analysis also. So we know that section is non-compact, and we have also calculated all of these values, KT, KL, and KR. We have checked that the value of the lambda e by lambda y, so the section under consideration is non-compact. So in here we can see that bending moment capacity that is coming is 126.64, which needs to be multiplied with 0.9, we can say, to find out the value of the effective bending moment capacity. So I hope this is also simple calculation, that how we can do this particular calculation in the ETABS and in the manual calculation. So in continuation of this particular the cantilever beam analysis, we can just simply uh, discuss that how we can design the laterally supported cantilever beams also. So just as a we can say theoretical, we can say practical analysis, we can just simply save as this model. So we can select this particular beam and we can go to the design, steel frame design, and lateral bracing. So in here we can select the user specify uniform bracing, and we can assume that the whole beam is laterally supported at the top. So we can run the analysis again and see the difference, that whether there is any substantial difference when we're dealing with the laterally supported and unsupported beam, considering the cantilever beam effect. So we can just left click on steel frame design option here. So in here we can see that more or less the results are same. That is approximately the major bending moment capacity that is coming, that is approximately again 114 kilonewton meter. The reason why it is same is because the calculation that we had done here, that is, we can say that the MS value that we had calculated was basically Fi into ZD, that is 126.8. And if you're talking about the laterally unsupported beams, if this multiplication factor, that is alpha m into alpha s, that comes out to be less than 1, in only those cases there shall be difference in the bending moment capacity of laterally supported and unsupported beams. But in here, if we are taking this value as 1 and we are multiplying it with ms, which is basically the bending moment capacity considering laterally supported beam behavior, that is considering full elastic section modulus. So that is why we can see that there is no as such difference here when we are dealing with this kind of laterally supported beam behavior. So I hope the concept is now clear to you, that how we can do the calculation analysis for cantilever supported, cantilever laterally unsupported beams, and what are the theoretical calculations that needs to be done to for the cantilever beam behavior.